we are just about ready to get started here. I'm having my usual struggle with the projector. I thought I figured out what the green button meant, or the green light. I thought that was going to work, but apparently I've been outsmarted again, so I'm just going to give it a second and see if it's rebooting or if I need to push the button one more time. But just as a sort of our usual recap of what we covered last time, we had started talking about research in general, and different kinds of research and different ways of collecting data. So that was a pretty good start to things. We focused in mostly on our descriptive methods, where we were looking at how we can describe or compare things but not manipulate them. And that led us to today, where we're going to start talking about experimental research, which is all about manipulating things. So hopefully that's going to power up shortly. It says it's green. That sounds promising. All right, since I assume it's just seconds away, I'll start, because it's just off that first slide talking about experimental research. And our first definition for today is that an experiment is when you have the manipulation of one or more variables under controlled conditions so that the resulting changes in another variable can be observed. So we're going to talk about one of these sort of simplest versions of an experiment just for the example's sake. I will show you a couple of sort of brief examples of what happens if we add in extra variables that we manipulate, or what if we add in extra variables that we measure. But for the most part, we're going to be thinking about simplistic, one manipulated variable, one measured variable kinds of experiments. And as hopefully you've figured out by this point, having gone through all of that descriptive research methods, all of that stuff, we couldn't make a causal conclusion because we weren't actually controlling enough factors. So that's why we've been leading up to talking about experiments where we can actually show and be more certain of that causal effect. So we'll see that these are important for detecting cause and effect relationships. You might also just see it that it's a causal relationship, and all that's saying is that thing A, the thing that we're manipulating, is going to cause a change in thing B, the thing that we're measuring. And we'll get precise terms for all of those in a moment. All right, and so I've kind of hinted at these definitions coming up, where we talked about hypotheses and theories, where the theory is more of a broad collection of ideas, and the hypothesis is a specific prediction tested by each experiment that's conducted. So we're designing experiments to try and test the bigger picture using very precise predictions. And that's the relationship between those two. So I actually did a formal definition for both, where a hypothesis is when we have that tentative explanation or prediction of some phenomena. So maybe we have the idea that when we manipulate A, it should cause a corresponding increase in B. So increasing A causes an increase in B. That's a hypothesis because we have a prediction of what we should see if our theory, our understanding of how those are related, are actually related. And then the theory is going to be a more set of formal statements that explains sort of how and why those events might be related to one another. So we might say that A causes a change in B because of some way that they're related. That's more on the theory side of things. So the theory explains why, but the hypothesis is focusing in on exactly what we would expect based on that theory if we did a particular manipulation or change. And that's another one of those really good questions to ask you about is, can you verbalize the difference between a hypothesis and a theory, especially since this is probably the second, possibly even third time it's come up in this lecture. So a really good one there. And so if we're going to talk about what makes a good theory, what makes that overarching explanation that we have a good one, there are a couple of different criteria that are useful. A theory doesn't have to have all of these, but this is sort of a good place to start. This is us saying that we're going to begin with a theory to explain something, and then as we do more and more experiments, we can adjust that theory according to what we've observed. but this is our starting point, and these are things that are helpful to start with. So the first thing you want to make sure is that your theory is actually consistent with prior observations. So does it lead to predictions that are supported by the existing research? So if our overall theory was that A and B are related because of some external factor, then would that match with a specific prediction that we could make based on other experiments that have tried to test that theory before? We also want to make sure that our theory, at first at least, conforms to the law of parsimony. And so parsimony can also be called Occam's razor, but you've probably heard it explained as the simplest explanation is usually the best one. And the reason why we use this in science is because you can come up with a whole bunch of different stories that might explain a relationship. If we don't know a whole lot about A and B, we can come up with all sorts of explanations ad hoc, which just means without any prior experimentation. But in order to sort of have a grounding place to begin, we want the simplest explanation. And that's where Occam's razor, or the law of parsimony, comes in. It's where we start with the most basic, direct relationship between those two things, and then if our experiments, if our individual hypotheses are not supported, then we might have to change and reevaluate our theory, add in some complexity, but we start simple and build up, as opposed to starting really complex and breaking down. It's just giving us that roadmap of where to start. We also want a good theory to be as specific as possible. We'd like to explain not just that A and B are related, but the nature of that relationship, because you need a pretty specific idea of what's going on if you then want to be able to make a precise hypothesis about what might happen if you manipulate one of those variables. We also need that to be measurable. We've talked about empiricism and that gaining information from observing. You can't really observe the outcome of an experiment if you can't measure any part of that experiment. So for this reason, a lot of statements that don't have sort of a concrete testable component can't be considered theories because they're not something that we could actually test. So a good theory should lead to specific hypotheses about what we should see in a particular situation. We'd also like, though again, a little asterisk there, that it's ideal to try and establish causality. We will find that sometimes it's just not possible, sometimes we can get close, but that's the goal. We want to be able to show that if we control for everything else, we can see that relationship directly between A and B. But yeah, that's sort of an idealistic thinking. And then to go along with our measurable idea, we also want something that is falsifiable. So if you can quantify it, if you can measure it, you should also have things that you could measure or quantify that could go against your theory. So again, in that line of empiricism, we want things that can be observed and tested, and there are some statements that just cannot be tested or quantified in a good way. So whenever we're looking at theories, we're focusing on as many of these factors as we can. All right, so the next thing is actually a couple more definitions, and these are when we're starting to name our variables. So instead of just calling them A and B, now we can actually give them a proper name based on their function or on their role in our experiment. So you might have heard these terms before, independent and dependent variables. I always struggled with these because they're very close together, but our independent variable, the IV, is the variable that the experimenter is manipulating. I focus on it being independent because it doesn't change based on other parts of the experiment. You have to physically change it, so it is an independent variable. Whereas our dependent variable is the variable that's affected by the manipulation of our independent variable. And that's if they're related. Sometimes you'll manipulate your variable and nothing happens because your theory was wrong, but that's hopefully less common. But I remember dependent variable because it varies depending on the level of our independent variable. And so when we ask that question of how does A affect B or X affect Y, we're talking about the independent variable, the first thing that we talk about. How does it cause a change in the second variable? So how does our independent variable, how do changes at that level change whatever we measure of our dependent variable? And then we can also talk about extraneous variables, sometimes also called confounding variables. And these are just other things that are going on in the background, uncontrolled events that can also affect our dependent variable. So if we were looking at, I'm going to draw a blank on that. I'll come up with a good example momentarily. Okay, so I'll go back to birds because I know birds. So we're going to look at song rate, and we're going to look at time of day. And they sing a lot in the morning and they don't sing a lot in the afternoon. Great. So if we pseudo-manipulate the time of day, as in we show the birds that it's morning or we show them that it's afternoon, they should change the dependent variable of how much singing they do. But I think I've also mentioned that birds are frustrating in that they also know what time of year it is. So season can affect when they sing. They sing a lot more in the spring than they do in the fall because spring is breeding time. So if we're not taking into account what season it is, that can be a confounding variable. Because it's something else that's going on, it can change the rate of singing, but it's not the thing that we're trying to control or change in the experiment. So it's something else that can be affecting our results. And usually we try and control for as many of those confounding variables as possible. But having worked with birds for a while, I can tell you that season is something that has popped up a couple of times. And now we typically run experiments multiple times a year just to be sure. So there's always a way around them. All right, so our next closely related terms that you are going to want to become familiar with are populations and samples. So this is another one of those really good questions to ask you to compare closely related terms. But with a population, that's going to be the entire set of individuals that you want to draw conclusions about. So if I want to learn about university students in North America, that could be my population. That's who I want to learn about. But I can't study every single university student in North America. That's just not feasible. So instead, what I would do is take a sample from that population. So I would take a subset of individuals from our larger population in order to be able to do my experiment with those people, and then hopefully draw conclusions that would apply to the larger population that they came from. So the population is the big thing that you want to study, but the population is what you are left studying. It's what you end up physically studying. And your sample has to come from your population if you want to draw conclusions about that population. And we also want to get a good sample, because if you use different methods of taking a sample, sometimes you're not going to get a good representation. So let's do a little thought experiment. We'll stick with the universities. So we want to study university students in North America, but I only have access to students at the U of A, Grant MacEwan, and here. So that's what I have available. So I could draw my sample from those universities, but that kind of gives us a limit on what we could apply our findings to. Maybe there's something about being in Edmonton, or being in Alberta, or being in Canada that would be specific to our sample that wouldn't necessarily hold true across the whole population of university students in North America. So we have to consider that in that situation, our sample is not representative of the population as a whole. We've somehow, we know how, selected a biased sample. So our sample isn't going to let us make a good connection to that bigger population because we didn't pick it in a good way. And so on the next slide, we can actually look at a couple of different ways for picking our sample. Some of them better than others, but as you'll start seeing, sometimes you're limited based on what you have available to you. So The ideal situation in most cases is to use simple random sampling. And as the name would imply, you're basically going to choose at random from the whole population available to you. So in that case, everyone in the population has an equal chance of being selected. So if you have 100 people that you have in your population, every one of them has a 1 in 100 chance of being chosen. So it's all equal. We can end up with a slightly modified version of that, which is a stratified random sample. Now this is usually used when you have a particular group within your population that's much smaller than the whole population. So if you have maybe you wanted to look at, again, the university students, and most students in North America go to English-speaking schools, but there are some who are primarily French-speaking. So maybe you want to make sure that you actually get some French-speaking students in your sample because you care about their primary language. So you might use a stratified random sample and actually divide that population into subgroups of what you're interested in. So French universities and English universities. And then you would take representative or random samples from each of those groups separately based on their proportion of the population. So if there are 100 English-speaking schools and only 10 French-speaking schools, then you're going to take proportionally the right amount of students from each randomly to have sort of a 100 to 10 ratio in your sample. So you can you're like controlling at least one stage of it to make sure everyone is equally represented. So you've lost a little bit of randomness, but we've accepted that making sure that we have that underrepresented population present overcomes any representativeness we would have lost by not being truly random. So that's sort of one of those, you make the decision based on how small of a subgroup you're interested in. The next is going to be a broader category, and these are when we're getting into the ones that aren't great to use, but sometimes have to happen. So you can talk about non-random samples, and actually number 4 is a type of non-random sample. We're just sort of talking about it separately because it's one of the most common. But if we talk about a non-random sample, we're basically saying that there are non-equal chances for everyone in the population to be in that study. There are a bunch of different ways that you can collect non-random samples. You can use things like a snowball effect, where maybe you want to study people who have loved ones who suffer from cancer. So maybe you go to a grief support group and talk to people whose loved ones have cancer and ask them to reach out to their friends who are in the same situation. It's really, really useful to do something like that, again, if it's a very rare population. It's really hard to randomly find people whose loved ones have cancer, but you can use sort of a biased sampling method to get more people involved. So that's, again, one of those times where it's not random, so it's not ideal, and not necessarily representative of the population as a whole, but with what we wanted to study, that's the only way to do it. So there's lots of different ways you can have non-random samples. We don't really need those for this class. If you go into a methods course, we talk about them a lot. Convenience samples, as I said, are a type of non-random sample, and they are the ones that look worst on paper, but actually happen the most often in real life, at least from my observations. And this is where you work with what you've got. So with the universities, the example I used at the beginning, where I have access to the people at Concordia, U of A, and McEwen, that's a convenience sample, because that's who I would have available to me. I would probably contact their psych departments and be like, hey, can I get access to your undergraduate research pool? That would be convenient. And again, so sometimes you can accept that it's non-random, but other times we need to keep in mind the implications of it not being perfectly random. And we actually have a couple of slides on that in just a moment. But I've already kind of introduced the idea of then a representative sample. So that's a sample that represents the important characteristics of the population that you're interested in. So university students for whatever you're studying, maybe people from different countries, what language people speak, whatever. You can choose whatever groups that you need for whatever it is that you're studying. And the idea is that random sampling, if you have everyone in the population has an equal chance of being selected, the odds are that your population and your sample should match. So random sampling should get us a representative sample unless there are special circumstances. And I already mentioned one of those, being a very small subgroup might get missed just by chance, which is why we have that stratified version. But just for those who are visual, we can look at an image here, so a pie chart of A through H different groups within a population. Our bottom pie chart is a sample that is representative of that population, and you can see that each slice of the pie is about the same size. So they've done a good job, they probably randomly sampled, and they have a good representative population. Our pie chart on the top is an unrepresentative sample. Group A has been over-proportionately measured. Maybe they were just easier to have access to, or maybe you had some kind of bias in your sampling method, and that could lead to a situation like that. And that's problematic because if you're conducting research, you're going to have data that comes from a group that is sort of over-proportionally represented in your sample compared to that population. And so you have to keep things like that in mind when you're comparing the conclusions of an experiment and wanting to apply them more broadly. So we have to watch our external generalization, our ability to apply it to a larger population. All right, so again, I've kind of hinted at this, but it's not always possible to randomly sample. Sometimes you just don't have access to things. It's also not possible to have, say, an entire database that has every single university student in North America. There are privacy issues with that. So it's almost impossible to get a truly representative, truly random sample. So we'll sort of do the best we can. But we sometimes just have to design our research knowing that we can't have a perfectly random sample. And sometimes that's okay. So we have a couple of situations where it can be okay to have a non-random sample. And the reasons here are, the first is if the similarity of a sample and a population doesn't really matter. So if you're just trying to show that something could exist, so you're not trying to show a constant relationship or anything, you just want to show that this one event can happen, a generic statement that it can exist. Okay, well then you only need to see one case of it to show that it can exist. It's the kind of claim that you're making. You can also have situations where multiple experiments are conducted on different samples, and all of those experiments end up having similar results. So I want to make a conclusion about all university students in North America, but I only have access to Edmonton students. So I'll run a study using Edmonton students, and then I'll reach out to somebody in Nova Scotia, and they'll run an experiment on Nova Scotia students. And then we reach out to someone in Texas, and they'll run an experiment on Texas students. And if we all get approximately the same results, in the same basic setup, if our experiments are run the same way, but just on different people, then that gives us a lot more confidence that our results could generalize to the whole population, because we've taken a bunch of different samples from that population of interest, and even though each study on its own isn't representative of the population, when we combine them together, usually in something like a meta-analysis, where you can look at multiple different studies to get a better idea of the thing as a whole, that's a really great way to be more confident in your ability to generalize. And the last point here is that sometimes it's okay not to have a random sample if the similarity of the sample and the population is reasonable. And this is really important for stuff like brain scanning studies. If all you care about is the general layout of the human brain, then it doesn't really matter which humans you're looking at. So you wouldn't necessarily take, one from this university and one from that, and then from all over the place. It might just be sufficient to get a subset of whoever you have around and make a general statement that way. And of course, there are always going to be exceptions to stuff like this, but this is when we usually see acceptable deviations from randomness. All right, so next we can talk about what we do once we've picked our sample. We pick the population, we have our theory, the big overarching idea, we have a specific hypothesis, we know who we want to study it on now, so we've picked our sample, and now we would like to actually do the experiment. Most experiments are going to be set up with two different groups. And again, we're talking about the most basic of experiments, and once we get the basics, I add in ways to kind of change it up. But our two basic groups at the lowest level is an experimental group and a control group. Our experimental group are subjects, people from our sample, who receive some kind of special treatment in regards to the independent variable, the thing that we want to manipulate. Our control group is going to be similar subjects who do not receive that special treatment. So they are the control. We want to get a baseline from them. Sometimes you'll see the control group called a comparison group, because that's what you're doing. You're comparing between the experimental group and the control group. So both terms are acceptable. And we'll talk about sort of ways that we can change that up in just a minute here. Oh, yeah?
Would a control group also be like a placebo group?
Yeah. Which is actually 2 slides ahead. But our logic here is that if we have two groups that are alike in as many respects as we can get them, so if they are very similar from other factors, then any difference between the two groups comes from the manipulation of that independent variable. One group having received a specific treatment and the other group not receiving that treatment, the only difference theoretically should be that treatment. And how do we make sure that those groups are as alike as possible? We use something called random assignment. Now, I want to make sure that you can tell the difference between random selection, which is how we choose our samples from a population, and random assignment, which is what you do with your sample after they've already been chosen. So step 1 is the random selection to get your sample. And then once you have your sample, you want to split them into the two groups. You want to split them into our experimental and control groups, but you don't want there to be extra factors that might be different between those groups. The best example of this that I've seen is if you're doing, say, human participant research, and you're supposed to have 10 students show up. And you are like, okay, if there's 10 coming in, I need 5 experimental, 5 control. The first 5 that come in, I'll assign them to be the experimental group. The second 5 that come in, they'll be control group. But what if the ones that show up early are the ones who are really keen? They're really excited about the research, and they've shown up early because they're excited to be there. And what if the last ones that come in, or maybe some of them don't show up at all, then all of a sudden there's some other trait, the time that they showed up, that differs between both groups. And we don't know what effect that might have on the groups. So you really don't want to do that. That's where the random assignment comes in, where when they come in, you would have, say, some kind of random event, like a coin toss, or maybe you've put their IDs into your system and it just tells you what program to run, where you don't control it based on any other factor other than a random event. And then if we do that, the ones that show up early and the ones that show up late should be equally distributed throughout our groups. We can also look at other factors like age, because we didn't assign the older ones to one group and the younger ones to one group. By sheer chance, they should be about equally split between the two. And usually, if you're doing a good job with your experiment, you'll use that random assignment and then you'll check common confounding variables that might be a problem. Things like age, if you collect sex data or whatever. And you can just double check that both groups are fairly close to one another, because sometimes, again, by sheer chance, things will move just a little bit. So if we can randomly assign them, then we're controlling those extra differences as much as we can by that random event. And so any difference that we see between the two groups should be from that manipulation. And that does bring us to placebos, where, again, if you think about controlling extra things that might be happening, if we have one group that receives a treatment and one group that has nothing happen, they might figure out what's going on. If you have one group and you give them an injection and the other group just sits in a room, they're going to know that they're in the experimental or the control group because they can kind of figure it out. So what you might do is use a placebo. And the placebo effect is this idea that the effect of a treatment comes from the patient's expectations rather than the independent variable. So if we had that group that knew they received the injection, so they must be in the experimental group, maybe they expect to feel better because they know they got the treatment. So if we see an improvement, it might just be because they've reacted to what they expected. And the same with our control group. They might change how they feel based on knowing they're in the control group. And so that's the placebo effect, is our expectations influencing what we can measure out of them. So a placebo itself is the way that we control this. So we can then use some kind of a little bit of deception in order to equalize those situations as much as possible. So if you have the experimental group gets an injection of an experimental drug, maybe the control group gets an injection of saline. So they still get the injection, they still think that they've received the treatment, or they don't know if they've received the treatment or the control, depending on how much you can tell them. But they still get the injection, they get all of that. The only difference between the groups is whether they got the drug or not. We've now controlled for their expectations, so we're, again, removing extra variables that might be influencing our results. And so this can be all sorts of ways. You can use like sugar pills, you can use saline injections, you can have things like if you expose one group to an article that's supposed to manipulate their political views, maybe you expose the other group to an article that has nothing to do with politics. So they both had to read a boring article, but one manipulated the thing that you wanted it to, and the other one didn't change anything. So that's kind of the stuff you need to keep in mind in the background, and all of this is mostly driven by controlling those extra variables. All right, so that's our base understanding of experiments. And there are tons and tons of variations that can be done. As we move through this course, we'll talk about other experiments that have been done and different ways to sort of modulate a standard experiment. But I'm just going to touch very, very briefly on a couple of the most basic of those changes. So the first thing that you can do is expose a single group to two different conditions. So if you think of our conditions as the experimental group had that experimental treatment and the control group had the control treatment, that's two different conditions. But if you're really concerned about any background differences in the experimental group and the control group, things unrelated to your independent variable, maybe you want to control extra variables. Maybe you want to do a repeated measures or within subjects experiment. And I'll flip to a slide so you can actually see those written out. Actually, yeah, I can do that right now. So that's the one on the bottom, repeated measures or within subjects design. And so what happens in that situation is instead of having a group of participants and those get the experimental treatment, and then a separate group get the control treatment, now you only have one group. And so you're only working with one group of subjects, and what you're going to do is have that group exposed to both the experimental treatment and the control treatment at different times. Usually what you'll do is actually divide your group in half and have half of them receive the experimental treatment first and then the control treatment, and the other half would have the control first and then the experimental treatment. So it's still kind of separated out, but they're all getting the same treatments, just in different orders. So that would be a repeated measures or within subjects design. You can also use that to collect sort of the same information but across longer periods of time. That's again repeated measures. So that's one great way to do it. And that's, again, going to help you control those extra variables, those confounding variables, because your groups, the people that you are testing with, are the same because you don't have two completely different groups. So they can be their own control, and you can compare their own value with the control treatment to their value with the experimental treatment. So they act as their own controls, and you get to hold everything else in the background constant because they're the same people. And I suppose I should clarify that the between groups or between subjects design, that's the standard type of experiment that we've talked about. And that one's a little bit easier to remember because you have two different groups and you want to compare the differences between the two. So that's where that comes from. Oh, and I have a visual for that. I always forget that I include visuals sometimes for these things. So if that explanation of subjects and between groups or within groups, this is another way to break it down. So our between groups, our normal experiment is you have one group, they get the treatment 1, experimental treatment. Another separate group gets treatment 2, the control treatment. And then you compare between the two. Or at the bottom, it's one group, and they get treatment 1, and then treatment 2, or you can switch it up. But it's always the same people. So that's the visual for that one. All right. Our second point is that you can manipulate more than one independent variable. So instead of just manipulating one thing, instead of changing one thing, maybe you change multiple things. And this lets us look at interactions between variables. And I do remember that I have an image for this one. So this is an experiment where they wanted to look at the effect of cell phone use on driving performance. And so in the first part of their experiment, they looked at an experimental group where they had people on a phone, talking on a cell phone, and using a driving simulation. And they would measure their performance of driving was how quickly they stopped if an obstacle appeared on the screen. The control group didn't talk on a cell phone while they were doing the experiment. So they just drove and then stopped when the thing came up on the screen. And so from that first simple experiment, they found that there's a little bit of a delay in how quickly they stopped, so it took them longer to stop when they were distracted by talking on their cell phone. But they wanted to add in another potential variable that might influence this, and the reason was actually because they didn't see as large an effect as they thought they should. And so what they did was add this second variable here, a second independent variable, which is traffic density. So instead of just having them driving on an empty road in the simulation and having a deer pop up on the screen, now they had other cars around them. So in the first of our conditions for variable 2, they had low traffic density. And so here, people were broken down into ones that were just driving, so no cell phone, and the ones that were on the cell phone and driving. So distracted and not distracted while driving, but in low traffic conditions. Then they did the same with high traffic conditions, and they looked at some people who were driving with no cell phone and some with a cell phone, and how their performance changed there. And this could be set up as a repeated measures. You could look at the same group of people and test them in all 4 conditions. You could have 4 separate groups and compare between the groups, depending on what you have available to you. The convenient part there is the repeated measures one. If you only need one group of people, you need a lot less people. So sometimes that's really useful, and then you would just have some of them do 1, 2, 3, 4, some do 4, 3, 2, 1, you randomize. But here we see that there is an interaction between our cell phone use or no cell phone use and traffic density, where when we just look at our low density traffic, there's not much of a difference between the distracted drivers and the normal drivers. They're pretty close. It's a little bit slower to stop, but not a really big difference. But if we look at high traffic density, if we add that extra factor in, all of a sudden it's a massive time difference. It takes them a lot longer to respond because of all the extra things going on. So we would say that here, there's an effect of distracted driving or non-distracted driving, but there's an interaction with that effect and the traffic density. So that's one of the best ways that we can use these multiple independent variables. It gives us a chance to find how things interact and work together. And then our last point is that we can actually use more than one dependent variable. So instead of just measuring stopping speed, maybe we measure something else that might also be affected by distracted driving. Maybe we measure how often they look at their mirrors, or maybe we measure how consistent their speed is. By measuring more than one dependent variable, we actually get a more complete picture of what that independent variable, what our manipulation might be influencing. So it's giving us a better picture of everything as a whole, and sometimes that's really great, especially if you're not sure what to expect from your outcomes. All right. And then that brings us to our advantages and disadvantages of experimental research. So advantages, the biggest one there is always going to be that implication of causality. This is, like we said, one of the only ways that you can reliably assume causal relationships. So this is what you have to do pretty much in order to get a cause and effect relationship shown. The disadvantages, these are pretty logical ones, I hope. So experiments, you're trying to control for as many things as possible. So that's moving you further and further away from how these behaviors would occur in nature. Because you're controlling so many factors, it's a very artificial environment. And so that can limit how much your results actually apply back to the real world, which can be problematic if you want to apply those results to the real world. We also have to keep in mind ethical and practical issues. On the ethics side of things, you can't assign people to be in certain conditions. If you wanted to look at the effect of malnourishment on growing up, you can't assign some infants to be malnourished and some not. You'd have to do a correlational study where you measure those who happened to be raised malnourished and you compare it to those who were not. So you can't do certain things experimentally because it's not ethical. It's also sometimes not practical, especially with psychology. If you're looking at teaching someone how to do something, you can't give them method A to learn how to ride a bike and then show them method B to learn how to ride a bike because you can't unlearn bike riding. So it's not feasible to do that kind of an experiment. So there's all sorts of disadvantages and things that we need to keep in mind in the background. So that's why, even though it's like, oh, but experiments give us that thing that everyone's looking for, not always. So that's where we're going to leave it for today, and then we'll start talking about what our results mean and what we can do with them on Monday.